So we are recording the class. If you have any problem, any issue with recording the class, with sorry, if you have any problem, please let me know. I'll stop recording and discuss that. If you're well, I'm assuming that no one has any issue with this, and we continue recording the class, and will be shared with you for your later references. In continuation of what we discussed last week, just as a review, as we did, we were talking about transformation. So what we did, sorry, we learned how to work with these homogeneous matrices. We learned how to build up these homogeneous matrices based on rotation and translation. And also we learned through examples how to write them down, how to actually transform movement in 3D space, or describe movement in 3D space using homogeneous matrices. And now we are going to use these matrices, these rotation translations, to describe a robot and robot movement. To do that, a very simple example here, as we did last week. So imagine you have two systems. You have two systems here. System X0, Y0, Z0. So what you have is system X0, Y0, Z0. And you have another system, which is X, Y, Z, or X prime, Y prime, Z prime, you know, this system here, as you can see. All right, this system. Well, in this system, in this one, I have an object, or I have, well, something with a 3D shape. Now I apply some changes on this, just to you know, to give you an example. Like end effector of a robot starts moving. Okay, I know that end of the arm of the robot, in terms of coordination, where is it compared with the base of the robot? Now these changes which I'm doing at the end of the robot's arm are in this system. I want to find relationship or coordination of the object and orientation of the object, well, versus the center of the base system. So what we do, well, with that object, we wish to rotate the coordinate frame X, Y, Z for 90 degree in the counterclockwise direction around Z axis. So here we are rotating to this, as you see here. Yeah, this one, we're rotating that. Then we displace the new frame for -1 along X prime, 3 units along Y prime, and -3 along Z prime. So what we do, we come here. This is, well, this is the Y. This is the Y, the X, and the Z coming. So we are moving in this direction. After one rotation, we are moving in this direction. Then it says the frame will be finally rotated for 90 degrees around X second axis, which is this. So we do another rotation to convert it to this. So to describe this displacement from here to finally to point 4, we use matrices. We have, see, 1, 2, 3 changes in the location. changes in the location and orientation. That's why I have H1, H2, and H3. Okay, so originally I'm in a location. What is this location? This location is here compared with base system. So I have this far, this high, right? And well, this distance in this direction. So I am in a location, well, we show that with an H. So this is the original location of the object. Then, as I said, we rotate 90 degrees around Z. Then we translate that to a -1, 3, -3, transformation movement, linear movement, and another rotation for 1, 2, and 3, as we did in the previous one. So writing this based on what we learned for the matrices wouldn't be difficult. I have 90 degree, this one, translation movement, and the other 90 degree movement. So for 90 degree, if you remember, there is no linear or translational move. Again, you remember that this part is part of the matrix and your rotation will be reflected in this part. Depending on how do you rotate around, is it around Z or X or Y, you will get with what angle, you will get different values here. So I have rotation 1, rotation 2, and rotation 1, translational move, and rotation 2. When you multiply them together, you get this matrix. So this matrix is this part. Now, what you need to do is finding H based on what you have between these two systems, between this and this. Okay, having these two together will give you matrix. So from here to here gives you matrix H. Matrix H. With this matrix H, then with 3 transformations, you will get this. So metric, this is what we had for D, and this is my H. Y, look at this. This is the 2, you see, -1, and also 2. That's why you have 2, -1, 2 here. 2, -1, 2. And rotation, if you look at these two coordination system, this second one, top one, this one, and this one, you see it's not only just has a translational move, also has been rotated. You see X, you see Y, you see Z, means it's rotated around X. It's rotated around X for 90 degree counterclockwise. That's why you have around X rotation. You see X is 1. So what you have is cosine Y, negative signs, cosine theta or alpha 90 degree, negative sign, cosine, negative sign, and that's why you have this value. So it's cosine 90, negative sine 90, sine 90, cosine 90 for rotation around X counterclockwise. Okay, which gives you the final matrix here. So now, whatever you have, what is the use of this? If I clean here and to try to explain why this is a big achievement, now think about that. If on this object, if on this area, you want to do some specific movement, it can be any shape on this. You need to tell your robot, the coordination of that. What is the location, next location, location can be painting, can be welding, can be anything. You don't need to repeat everything so you have the matrix, you have the coordination, you multiply that coordination to that matrix, and you find the a coordination of the new point just using one matrix multiplication. You can convert every point on that object from the system to another system. If you want to convert it from from your system to your end effector to the base system, you multiply. Otherwise, you multiply it by invert of the matrix. Invert of the matrix to find it. Any question on this example, which we didn't finish last week? Any confusion? Good. Very, very good. And as I said, a general method for Denvit Hardenberg representation, it says when I have a sequence of changes, which we have in robot. In robot, what we have, when I have a joint 1, joint 2 connected, and joint 3 connected together, what we do, we try to build transformations based on two basic 3D movements: rotation, and linear movement. Linear can be fixed or can be can be something changing. You know, this point versus this point is changing one fixed part plus one variable part. I'll talk about that in next few slides. So the whole idea is now I try to model my robot from one point to another point through links and joint. We have been trying to classify, we have been trying to create a model which we understand in math, and we can use mathematical models to do the calculation. What we call geometrical robot model. Geometrical robot model. A geometrical robot model is given by the description of the pose of the last segment of the robot or end effector expressed in the reference, normally base frame. So geometrical robot, remember that geometrical model, model is given by description of the pose of the lab position and orientation of the last segment of the robot, which is normally end effector, expressed in the reference base frame. The knowledge how to describe the pose of an object using homogeneous transformation matrix will be first applied to the process of the assembly. Sorry. As an example, consider a mechanical assembly consisting of 4 blocks, such as presented in the figure of the next slide. This one. So very simple model. I'm trying to start with a very, very simple model. What we have here is a base down here, base coordination system, and end effector or end of the arm of the robot. And we try to build a relationship between coordination system, this coordination system, and this one using a homogeneous matrix, like we did before. A frame is attached to each of the 4 blocks as shown in the figure. Our task is to calculate the pose of the frame x3, y3, z3 with respect to x0, y0, and z0. Again, this one. x3, y3, z3 versus x0, y0, z0. Okay, look at coordinations. What we have here, you see I have this system here, I have another one here, I have another one here. See, so what we do, we find transformation from point z system 0 to system 1, from system 1 to system 2, and from 2 to 3. So it would be h, like what we have here, from h 0 to 1, from this point to this point, h 0 to 1. And from here to here will be h 1 to 2, and from here to here will be h 2 to 3. Okay. Now, before I start, and we'll talk about the matrix. Can you just look at this and help me to figure it out? From O0 to O1, from system 0 to system 1, what do you see? Is it translation or rotation? Translation or rotation? You see both? You sure? Two rotations? So look at this. Definitely, when since I have this movement, and look at the dimensions here. So it's 4 this way, and I have 2 this way as well, and I have 10, and also thickness of this is 1. Oops. So in this, so I'm going up like 11. I'm going from here to here with 4 and 2, 6. Is there any linear movement from in this direction, in x direction? How much is it x direction?
It looks like nothing.
Looks like nothing. It's moved alongside y and z. So my y has moved like for 6, and z has moved, so instead of that, has moved for 11. So in terms of movement, we have movement alongside x and z. So if I move this coordination system 6 units alongside y, positive y, and 11 units alongside z, what I get would be this system, exactly this system, like that. So it's x, y, z. What do you have is this. How do you convert this to that? What happened? Z. So definitely there is a rotation. I agree, 100%. There is at least one rotation. Can you tell me what is a rotation?
Rotate Z negative 90 degrees. Around
X,
Z.
around Z. Z has become this. You see, this is Z. This is your new Z. This is your new Z.
Yeah, if you rotate the translated vectors around Z negative 90 degrees, and then you have another rotation after that, you should get to what you need.
Okay, so you're suggesting that with two rotation, we can get there. So, and well, I'm just writing down this suggestion. Okay, I'm not making any judgments. So, Nikita and Paul and Jason suggesting that rotate around Z for 90 degree, then rotate around Y. Okay, Jason is suggesting X and Y. Let's write it. Okay, I write it and just get vote, right? Rotation at X 90 degree times rotate Y 90 degree. And Nikita suggests, Nikita agrees, or are you saying no around X and Y?
Yes, I agree with Jason. Rotate
With
around
J,
X and Y.
X and Y. And Paul, do you agree? And others also come in, please. Do you agree with this? No? Jude, yeah. Says X and Y with 90 degree, same thing. Could you actually have multiple option because there is two rotation? Yeah, sometimes it might happen. Well, yes, we can think of examples of when two rotations or different kind of sequence of rotation end up to the same answer. Well, I imagine it's possible, you know, like more hand. There are different ways of, if the rotate z then x, it could be the same. Oh, all right. So you're suggesting that rotating around z for 90, positive 90 or negative 90? Rotate around x will be the same. Both positive. All right. Okay. So that's how we do it, right? Finding different coordination. Here, this coordination is kind of weird. I wouldn't do that. You know, the rotation, I don't see the point why I should rotate this. But this is an example. This is just a very simple example to do a practice coming from the book. So when we write it down, it comes as this, right? So what we have is, well, for x, we figured that for x there is zero movement, no movement in x direction. We agree with that. And so this is correct. And in terms of rotation, what you see here in this matrix is two rotations. Well, there are two rotations here. Look at this matrix. No, it's just one rotation. Sorry. It's one rotation around Z, one rotation around Z with, I think it should be more than one rotation, -1, -1. It's impossible to have -1 unless you have negative, let me see, Z, X, Y. You have to do two rotations based on what I see here. Y, X, and Z. But it's suggesting, based on book, it's suggesting rotation around Z, which will be cosine alpha, cosine alpha, sine alpha, sine alpha, cosine alpha. So what we have from Z to, all right, I don't know. So let's try what we had. Let's try what we had to see if we end up to the same answer or not. If it's the same answer, great. If it's not, so what we got from book is not correct. So because we're doing that based on what we see. So it was rotate around x 90 degree times rotate around y 90 degree. Okay, let's double check that. So around x, we rotate down 90 degrees, y goes up. Why this is correct? We didn't check that together, all right? X and y. If you rotate around x, what you get is you're rotating around x, what it is. So if I have the system X, Y, Z. If I rotate around X, X will be at the same situation, and this becomes X, Z, and Y. This is after rotate X with 90 degree. And then if I do another rotation around Y and 90 degree, what I get is, again, counterclockwise will be X, Z, Y, which is not this. So I think that, well, it doesn't end up to the right answer. I think this answer is wrong. This is not correct. Rotate X 90 degrees. So Nikita, Jason, any suggestion? No suggestion? So we have to be careful with rotation. So this one wouldn't end up to this system. Let other rotations. Let's try other rotations. Okay, let's try other rotations. So what I have here is here Y. So if you rotate X 90 degree and rotate Y 90 degree. So if X negative 90, if X negative 90, all right. So if X negative 90, so I follow that, it will be Z, this will be Y, this will be X. This is rotate X negative 90. Okay, so I have Y down. I have Y down, correct. I have X, right, correct. And now, if with Y I rotate positive, so rotate with Y positive 90, means you're rotating this way. So your Z will go here, your X will be here, your Y will go here. Right hand rule with 3 vector in 3 dimension is pretty tricky. I agree. So our rotation, so I have to correct this with negative 90, So that will work. Convert this system after rotation to that system. Now, let's apply that. Let's apply that to find out what we have, okay? So rotate around X with negative 90. Rotate around X with negative 90. So I'm not touching this. Okay, just a rotation. What is the rotation here? So it's around X, means I have X here, and well, 0, 0 here, and 0, 0 here. The only 2 components I need to consider are X and Y. Just if you remember, it was X, Y, Z, 0 between this system and the other system. Paul says that 90, then X negative 90 should give you the same result. I agree that there might be other answers. I haven't checked that yet, but there should be other solutions as well when we are rotating the degree after 2 rotations. We can double check that, but let's finish this to make sure that we are getting the same matrix as we have in the book. Okay, so the values are, so X, Y, Z, so it will be cosine of negative 90, C negative 90, S Uh, could there be a rule like when you have equal rotation about two axes where it can be multiple answers? Multiple answer. Well, the rotation is basically just sorry for will interrupt my explanation. Remember that in rotation we have repetition in its nature. Okay, so this is what you say for a rotating a 3D. Think about the rotation in two-dimensional. So if I have a point like that, I want to make it a point like this. How many different rotations from A to B, just with rotation? How many different rotations you can find that you get from A to B, Jason? Just two? But I tell you there are infinite number of rotations I can tell you can get from A to B. You can you can make a lot of different rotations, right? You can do it in 2 steps, in 1 step, in 3 steps, in 100 steps, right? You can come down, then go up, and you'll go further and come back. There are infinite number of rotations you get from A to B. So it is in the nature of movement, like going from point A to point B. How many ways you can do that in linear movement? There are infinite number of ways you can do it, right? Depends how we move exactly. And in the robot, the interesting or tricky part is our movement is limited. It's not like 100% freedom. Because of the links, because of the joints, you can't do every move you want, right? You have a limitation in your movement, and that limitation makes your choices limited. In terms of robot, it will be different. But mathematically, just looking at just free movement from one point, or a translation from one point to other point, I can imagine that there might be an infinite number of sequences that end up to the same transformation. But having said that, the matrix, homogeneous matrix you will get will be the same, should be the same. It's something that you even if you do it through 10 different rotations, you should get the same answer. That's the part. And in this class, we are not making this. We are not talking about the geometry in or 3D coordination system in general. We're talking. We limit our discussion to robot. That's why I'm not, elaborating on how many different ways you can do it. But for robot programming, sometimes it's important because with limitations you have with robot, but still there are many ways to move from one point to other point, depending on how do you want to do it, how fast, how accurate, or what pathway you should go or should not go when you're programming a robot mathematically. Okay, so let's continue on this. Sine of negative 90 and sine of 90 and cosine of negative 90. Negative 90, yeah. That gives me sine of negative 90, negative 1, 1 will be 0, negative 1, 1, 0. Okay. The other one, same thing. 2, 3, 1, 2, 3, 1. We are rotating around y, therefore this will be 1, 0, 0, 0, 0. What you have is z and x, z and x. So for z will be cosine of 90, which is 0, and negative sine of 90, which is negative 1, and sine of 90, which is 1 and 0. Now you apply these two together, and you should get the answer. When we multiply these two together, we should get that matrix. Do that, please, at home, and see if you are getting the same answer as we have in the book. If it's not the same, come back to me. We can double check it. Either something is wrong with the book or with our calculation. So I want to comment on this. I don't want to just take more time on this. Any question, any confusion on this? So in brief, I just want to summarize very short what we did. We were looking on a homogeneous matrix how to move from here to here. We figure out that to move from here to here, what we need to do is 2 rotation and 1 translational movement. For translational movement was was straightforward. I'm sorry. Movement, linear movement is straightforward. Based on dimensions we see here, we can figure out in what direction, how long to go to move from O0 to O1. For rotation, however, we found it is slightly tricky and we can do it. This specific coordination O1 cannot be found directly from O0 unless you do 2 rotations around X and Y, and we had suggestion as that it might not be unique sequence of rotations. You can do it with 90-degree around X, 90-degree around Y, and also we have suggestion you can do rotation around Z and rotation around Y or X based on suggestion you saw here. Any question? Very good. And I hope, and well, I think it should be when you multiply this to this, you get this matrix. So I hope you have this. So I take it out. Okay. You don't? Oh, you multiplied and you don't get the same thing? That's painful. Okay, you're making me multiply it. All right. So I'll do it. Okay. So I just multiply this line in this. I'll get 0. Okay. I multiply this in this. I'll get 1. Okay. Let's see. Yeah. More or less, I'm getting same. It seems that I'm getting the same thing. The second one will be 0, and well, here is 0 anyway. The second row, when I multiply, I get 1 here. When I multiply this to this, I get 1, 0, 0, 0. And third one, when I multiply, I get 0, I get 0, I get 1, I get 0, and 0, 0, 1. So that's what I'm getting. And yeah, it's different from what I see here. From what I see here, it's different. Well, I don't want to take this out, but yeah, these two are not the same. Well, regardless to that, this is easy. We can replace those. 1, 0, 1, 1, 0. Not the same. Okay, so might be something wrong with the calculation of the book. I don't think we did a mistake because what we say makes sense based on what we see. So don't worry about that. Probably it's something, it happens in books. Sometimes they do mistakes, okay? But you understand how it works. You understand how it works and how it's implemented in a robot coordination system, okay? So secondly, when we want to move from here to here, now from here to here, again, I have some movement, linear movement. As you can see on Z direction, I have this plus this, which is 5. This is 5, and this is 8. So on Z direction, I have 13 unit of movement. In a Y direction, I have, sorry, in X direction, not Y, in X direction, I have this. In X direction, in total is, in X direction is 15. From here to here, right? From here to here is 15. And for Y direction, in Y direction, I think we have only one because of thickness of this segment. So it will be just one. So if I rearrange it, it will be 15, 1, 13. X, Y, Z will be 15, 1, 13. Shouldn't Z be 8? Why 8? Why
See
8?
the solid line goes 8 all the way to the other side.
Oh, you mean this? You mean this?
Yes.
Good point. Let me see. That's confusing, actually. It's
It'll
sorry.
be larger than 8. If you look at it proportionally, it should be larger than 8.
Well, I agree with. Well, I also agree that is slightly confusing. What I'm assuming is, since this 15 is just referring to the solid line, and this 8, so we assume that what we have is 8 here, and what we have here is 15, and what we have is 5. So if it's not, it's not our fault. It's just a representation, because this 8 is confusing. And also 5 can be, 15 also can be confusing. He mentions all the way or just from here to here. Well, let's check. 11, 1, 8. So I think it's 8. Yeah. So let's correct ourselves. So so it means that whole line is 8. And I think that means all the way here is 15. So length of this link totally from beginning to the end is 15. So, and yeah. So if it's 15, and I know that this part is 4, this part is 4, so X will be 15 minus 4, which is 11. And 8 from here to here means your Z is 8, and your Y is 1, still 1. But be careful, Y is going down, and you're adding 1 on negative side, so it will be negative 1, which is, so remember, for this measurement, what we have here is this 15 is from here to here, this 8 is from here to here. Thank you. So Jason was right. So our translation will be like that. Well, these books are not ideal. These books are not coming from another work writing that, and actually author asked me to give him feedback on mistakes or any problem if he has in the examples or in the book. So I can communicate with him about that as well, why you probably might be a mistake. So in terms of rotation, what do you think? Rotation, what I have is X, Y, Z. So this is X, this is Z, and this is Y. And what we have here is Y, still X, and Z. It's kind of obvious. negative 90 exactly. So if you do rotate, I agree, around x with negative 90, you'll get that. See, negative 90. So if I consider my thumb in the direction of x and I rotate it in negative, means clockwise around x, I will get the second coordinating system. So with that, with this, what I get is, so rotate x 90 degree, and also I have translation of 11, negative 1, and 8. What we get is 11, negative 1, 8, and rotation with 90 degree around x. As you know that since it's around x, means this should be unit. No change, 1, 0, 0, 1, 0, 0. So these two goes away, and this part will be cosine of negative 90. This is cosine of negative 90. This is sine of negative sine of negative 90, which is 9, which is 1. Sine of negative 90, cosine of negative 90, which gives me this. So this matrix is exactly the same as we found. Any question? Here, the confusion was the distances, well, which unfortunately was confusing. And the last one, from here to here, from 2 to 1, what I have is, well, in direction of x, I have 4, so x 4 in direction of x. In direction of y, here, can you see this? 1 by 1, okay, means in direction of y, I have 1, so y in positive 1, x is in positive, and y for y is positive as well, and for z I have from here to here, which is 5 plus 1. For z is 5 plus 1, which is 6. For x, oh, sorry, I think for x I made a mistake. For x is 4, and I'm going back 1. So it's 4 minus 1. So it's 3, it's 6. Let's check. 316. 316. Yeah, this time you were right. 3. And for rotation, what I have here is y in this direction, x in this direction, and z in this direction. Now what I'm getting is z in this direction, y in this direction, and x in this direction. You see, x is the same. X is the same. We are not changing x, but y rotates like that, okay? Like so. Are you sure it's 90 degree? Twice, yeah, twice. Okay, 180 exactly. 180 degree coming there. So it will be 180. So rotate around x for 180. 180. Everyone agrees? Positive or negative? You tell me. Positive or negative? Both can be. Yeah, both can be. Well, in real life, robot might not be able to do both. Just one of them is possible, okay? But in terms of calculation, it should be the same. It should be the same. Let's see if you get the same answer for positive 180 and negative 180, right? Let's write down the matrix to see what we get. For matrix, So I keep this will be 3, 1, 6, and 1. It's too big. 3, 1, 6, and 1, 0, 0, 0. Its rotation around X, I have here 0, 0, 0, make it clear. So cosine of 180. Cosine of 180. How much is it? -1, right? Cosine of 180 is -1. Sine of 180 is 0. Negative. Sine is 0. Cosine is -1. What if I do -180? The interesting thing is cosine of 180 is equal to cosine of -180. And sine of 180 is equal to sine of 180. Both are equal to 0, both equal to -1. So it doesn't make difference in terms of calculation. Will be the same. And that we expect that. We did expect that. Should be compatible with each other. Good. At last we did one correctly. Okay. Any questions so far? All right. Now we have this matrix H1, H2, and H3 transformation from 0 to well, these different points together. And now we want to find the transformation from here to here. To do that, the only thing we need to do is multiplying the three matrices to each other. So from 0 to 1, 1 to 2, 2 to 3, okay, when you multiply the three together, what you get is from 0 to 3 is this one. This is your well, homogeneous matrix transformation between base and manipulator or end of the robot or end effector of your robot in this system. Okay, any question? I think I made you tired, huh? Yeah, no, all right, okay, thank you. Okay, so geometrical robot model, in this case, the correctness of the calculation, orientation, and position of the third block O0 with respect to the base block O3 with respect to the base block O0 can be easily verified from this figure. So what I can do also, I can look from this to this right in this position. It's in this position. I can just look at what I have and how can I rotate it to get to this point easily just by well, checking X in this direction. That is like -1 rotation around Z. You see, in this position, to convert this to this, if I want to do it directly, the rotation is a rotation around Z with -90. Yeah, correct. -90, Paul. Thank you. And well, displacement, linear displacement is if you go from here to, well, it's kind of, well, you have 5 here. And you also, let's see, from here to here, right? This is in direction of X. I have total 8. Yeah, that's correct. I have total, red one, from here to here. I have 8 in total, okay, from this X to get to there. But there is one coming back here because of the thickness of the end effector or that link, so it will be 8 minus 1. So from here to this, instead of X, I have 8 minus 1. So X will be 8 minus 1. In terms of y, it's in negative, definitely, because it's going this way. And what I have is 15 minus this 15, this part, 15 minus 4 for y is in negative. It's 15 minus 4. And yeah, minus 4 minus 1 as well, because this is and going back minus 1, so it gives me 10. Is it correct or not?
No, if it wasn't 15 the whole length, or
Oh yeah, and it's 2. Yeah, you're right. 15 is the whole length, so it's minus 4 minus 2, because I have that part out, that part out. This is 4 plus 2. Okay, so it will be 15 minus 1, because of this thickness, minus 1 will be 8, but negative, because it's in negative direction of y. And for z, it's going, well, this is 10. From here to here is 10. Okay. But from here to here is 10. But I'm coming down like 5. Like 5. And I have thickness of 1 here. So it will be 10 minus 5 minus 1. Why? Because this is originally 5, but you have 1 here, which leaves 4 here. 4, 10 will be 6. So 7, 8, 6. 7, 8, 6. 7, 8, 6. Negative. Sorry, negative. Yeah, correct. So we can check this if we have it in a position, in a stand position, when there is no rotation. When you change it, if this robot starts moving, we can do that. We have to follow that the homogeneous matrix to find the new poles of the in terms of coordination system. But in this situation, we can check, we can verify what we did, which is correct, which makes sense. Okay, very good. Any question? Fantastic. Now, geometrical model of the robot. Let us imagine that the first horizontal plate rotates with respect to the first vertical block around axis 1 or angle theta 1. The second plate also rotates around the vertical axis 2 for the angle theta 2. The last block is long for the distance of d3. Okay, the robot mechanism is first brought to the initial pose, which was so-called home position. Home position is what we have, something like this. You have your angles and these linear movements all at 0 position. When your robot starts moving and rotating, actually this initial assumption will change. So will be theta here, will be theta, and will be a length d3 add minus, depending how do you move that. In the initial pose, 2 neighboring segments must be either parallel or perpendicular in the home position, in the initial position. The translational joints are in their initial position, assumed as d equal to 0. This is, well, you know that this is called SCADA manipulator, selective compliance assembly robot arm. And well, now the question is, if I have this theta and this d changing, how do I find the coordination system here versus here? Okay, that makes it when it moves, that makes it complicated or more. So the more practical shape for this robot will be something like this. If you have, but still dimensions, still calculations are similar to what we did originally on this robot. So when second block rotates around axis 1 and the third block rotates around axis 2, while the block is enlarged, along the axis 3, the robot is, well, we can, what we have is a scatter robot, So because of the displacement about axis 1 and axis 2 and along axis 3, the homogeneous matrix consists of products of first matrix describing the pose of the object and second matrix describing the displacement of the object. So what we do, again, similar, we build a sequence of homogeneous matrices to tell us what is the transformation from each coordination or each well, between links and rotation and joints of the robots. So well, in that case, instead of having fixed values, we might have variable values. You see, like L1, which is the length of L1. So here, as you can see, from this coordination system to this coordination system, okay, so if you have X, Y, Z, X, Y, Z, from here to here, the only thing you have is linear displacement, is a translational move. It's not moving, but it's a fixed translational change from this system to other system, which is L1 without any rotation, multiplied by a rotation which is possible because of the rotational joint. This rotation will be around z-axis, okay, around z-axis. Therefore, what you get is the rotation around z-axis. How much, depending on theta, you have. So it will be rotation. So what, from point 0 to point 1, from O0 to O1, what I have is translation of 0, 0, L1 times rotation of around z and theta. That's what you have. That's the concept of what we said before. If I go back here. And with Hardenberg representation. So now look at this representation. It says in a robot, from each joint to other joint, from each section to other section of the robot, what do you need is two sort of changes. One is translational, the other one is rotation. You can build up a simple geometric model for a robot by multiplying translation, rotation, as you can see here. So DH convention coordinate frame attached to the joint between two links, that one transformation is associated with the joint and the second associated with the link. So we have joint link transformation, one after each other, multiplying. So you see, because of joint link, after each other, what I said all here will apply to almost every kind of robots we use. So here, going back to my original. So here is moving from here to here with the rotation. So that will be your transformation from 0 to 1, from 0.0 or coordination system 0 to coordination system 1. From 1 to 2, from here to here, okay, what I need is just, well, from this to this, what I need is a translation like that alongside y with length L2 with no rotation, right? And one rotation, again, around, depending how do you define the rotation, around Z, around Z, around Z again, with angle theta 2. So here, L2 sits here, and cosine theta 2, the C2 means cosine of theta 2, and sine of theta 2, okay, with the rotation. So what I have here is translation from this to this, from this point to this point is translation with 0 L2 0 times rotation around Z with theta 2. That makes my robot second link versus first joint. Second joint versus first joint. And finally, from here to here, as you can see, we have another displacement with length L3, translation 0 L3 0 times another rotation or translation from here to here. What do you think? When I move from this coordination system to this coordination system, what I have, is it translation and rotation again, or translation? Here would be translation, another translation, because this joint doesn't rotate. This joint only moves up and down, up and down. So it will be translation with definition. Actually, how do you define that? It will be translation 0 0 and D3, or as it defined here, because it's going down, will be negative D3. So here I have translation times translation for this joint. When I combine the three together, from origin, from base to the end effector, what I have is matrix 1, matrix 2, matrix 3 multiplied together. So I have, after multiplication, I will get this answer: cosine of angle 1 and 2, sine of angle 1 and 2, and negative L3 times of sine of the 1 plus theta 2, and sine, and so on and so forth. You can find the relationship between your end effector and your base coordination system. Any question? No question so far? Okay, so I think we should have a break now, and continue after the break. Is there any question before we stop? All right, so I'll stop recording.